Alright, welcome. Another draft physics video presentation. Sean Carroll is, is making more content, which is good, but it's not very good content. So anyway, way overstatement here. The biggest ideas in the universe, and frankly, they're not very big ideas. And so far, as expressed by conventional physics, which has lame explanations for pretty much everything. So he's going to play with conservation of momentum, in the context of a universe where they don't conserve space. I mean, space is being made all the time. There's no conservation of space. It's not being destroyed somewhere. It's just being made, constantly making all this extra space to move everything flying apart. So I mean, the most basic motion in the universe almost is one they don't have a conservative notion of, and yet they'll use the word as if they have some sort of concern for the fact that the universe has to eat as much as it, poos. And it has to all go somewhere. Let's put it that way. And they don't really follow the bouncing ball very well at all, because they have no explanation for gravity or magnetism in terms of where the energy comes from, where the motivator is, and what the motivator is. And even things like, you get into this quantum mechanics stuff and their entanglement idea. So they're not even conserving experience. They're saying that this white chalk is going to have an experience, and it's going to decide to be white. Because of its experience, it's going to collapse at a certain point and be white. And regardless of what experiences this little piece of green chalk is having, it's forced to be green now. It can't be white. Even though its experience might say, you're going to be snake eyes, it's saying because this one rolled whatever, this one has to be something else. So in spite of its experience, it doesn't matter anymore. I'm going to force you to be something because something happened to this one over here. I mean, it's not even, they don't even conserve cause and effect. They don't conserve a causal universe. So anyway, it's just kind of ironic, in my opinion, that they would use, this is one of the ideas they've conquered when they really don't have that much respect for the concept of conservation of momentum or movement in the universe. They're not even seeing the universe the way it should be seen by physicists. I've said this like 100 times now, but it's something I wish they would have said to me in school. There's only one universe, and it's that really small universe. The empty space out there is the same empty space between electrons and protons. And the little stuff that obviously moves between them, photons, for example, or something else we know exists, is this kind of energy that's invisible. This little tiny stuff. And that is what causes things to move. That stuff hits something and makes it change. Its world changes. The world the little thing is in changes and forces it to move because it got pushed by something. Well, I guess I wish they would have just said it's a push universe. Yeah, I wish they would have just said that. That there are no such things as a force. There's nothing that everything's a straight line in the universe. Everything is a straight, nothing travels this. Nothing does anything like that on purpose, by design. It has to be forced to do it. And that's the conservation. If something forces this way, then there's something else in the universe going to force this way. If you consume right hand, you're going to have left hand somewhere loose. That's conservation.
Hello everyone, and welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll, and this is the first...
Right, so we'll just... I can't move along. I thought this was a good idea, putting the video in here, but there's no move along button. What's this little button do? Well, that didn't help much. Yeah, that's the don't hit it button. Okay, so I guess we'll have to do it this way. Unfortunately.
have been a somewhat fair accusation, but for Aristotle, it certainly was not. He was absolutely an.
So there's really much point, in my opinion, of going through this history of, who thought of it first or who said something like it first. Going back 4,000 years doesn't make much sense, or whatever. 2,500 years, I don't know. What's the point? I mean, there's clearly they didn't have all the information we have now to understand the universe the way it is, and and again, this idea of momentum, this idea that something collects a kind of energy by moving, that, and I would argue that it's better understood as, when you have mass, what it really means is you're pushing in all directions. So if we just thought of everything and just tried to make everything into a blob, you could sort of understand that the blob that you are is actually pushing on the universe in all directions. And that what happens when you move is this, if I give you velocity, is that some of your mass is no longer going that way and that way, or that way and that way, and I start moving it this way. I start changing which way it's going, your mass. And so then you have more mass going in a direction and less mass going in these other directions. And it sort of makes sense in the sense that obviously something gets very light in this direction. When it's moving this direction, it doesn't weigh very much. And as it's going faster and faster, it also doesn't appear to have much impact going this way either. It gets more and more invisible the faster it goes. So it's not reflecting a bunch of photons anymore either, because it's not around to do it. So your mass gets less in one direction, it gets more in another direction. So you're really conserving your mass in that sense, that you're not really piling in something. You're not collecting it and getting heavier and heavier and heavier. You're just getting heavier in one direction, the direction you're traveling. And that's the half whatever blah 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 rule, of kinetic energy. You're rearranging your mass as you accelerate. Now let's jump ahead from Aristotle. That's just kind of useless.
Also, even in perfectly healthy adults, the number of teeth is not necessarily constant.
All right, so telling stories about Aristotle getting something about teeth wrong, and it's like, well, what? Sorry, it's that's a rice cake in terms of food value. It's a rice cake bit of physics. I really don't want to eat one of those. I don't need that story, frankly.
A purpose or a want or a desire on the part of these objects. There was a state of...
Right, okay, so this is another thing they do, is they say something has a resistance. It's fighting the change. They use this kind of terminology, and it's just wrong. It's under a circumstance that's things don't have like, I want to stay in my inertial state. They're not really saying that. They're just saying, you have to motivate me. Okay, so you hit me with something and I'll move. But if I'm already being hit, if I'm already being pushed down onto a surface, well, yeah, it's going to be harder to push me because I'm attached to the surface. I've got a bunch of friction I'm going to create between me and the surface because you smashed me into it. I've been smashed into it. I'm still being smashed into it. So I'm going to be harder to push. So, I mean, this old idea, that somehow objects resisted motion, when no, they really don't resist anything. You have to apply a force if there's already a competing force. If there's already some other thing working on something, then yes, it's going to require you to apply more work to undo their work. So I'd say that's another place where they kind of misunderstand any like I said, the whole idea of thinking of it as resistance, when no, it's not really resistance. You just have to account for the other forces that are compelling something to do something.
Being that they found most comfortable, and they settled into them and stayed there.
Yes, and you've stayed there. So I would argue that you've stayed in archaic notions of reality where you haven't recognized that you have to account for something's behavior with something real. So if two magnets attract or they repel, you have to account for why they're doing it. You can't just say, oh, there's a magic force between them. and then just leave it at that. Not even describe how this force works. Does it radiate? Does it does it move at a certain speed? Oh, the same speed as light. Maybe that should be a clue that, like light, it's carrying momentum, this force, and this force has to be conserved. There's only so much of the force. The force is a something, and the force is manipulated by objects. Objects somehow manipulate the force. And the simple explanation, for example, for magnets is that the magnet is merely filtering the force. One kind of force hits here and it comes out of that end, and the other kind hits here and it comes out of this end. So like the magnet has a north and a south, the force itself has two different characters, and therefore you can filter it. And by filtering a force, you make the force more capable, because it's now pushing one way instead of doing the yin-yang thing. It's just doing yin, and then it's doing yang over here. You're separating the two right and left hands and their influence. Jump ahead a little bit.
His name is often Latinized to Avicenna, so you might know him under that rubric.
Who cares? Blah, blah, blah.
So most
go ahead
say
a little.
that he didn't have equations for it, but what he did was, he looked back at one of the issues that Aristotle had. So Aristotle knew that there were examples, because he was an empiricist, he did observe things. He knew that we all know of examples where things don't seem to come to a halt, at least very quickly. So consider an arrow flying through the air.
Right. Okay, so this is, again, why not talk about it in terms of what we know in the modern context? But this is where it also gets confusing, because there's this whole argument of what is drag and perpetual motion. So I would argue that the force demonstrates itself to be pretty perpetual, that we could probably agree with conventional physics that a quanta of energy, say inside of a photon, goes into a system, and that quanta of energy just doesn't disappear. It does something, okay? But it's going to keep doing something in the universe. It's never going away. It's just constantly going from place to place, doing something in the universe, and that it will never come to rest somewhere. It will never hit something and now it's not doing this anymore. That'll never happen. No matter where it goes, it's just going to keep moving. And that's the nature of the energy that's in the system, that you could call the forces and the rest of it. It gets its reality from the fact that it seems to be this perpetual element of movement that exists in the universe. Now, like I said, well, they probably won't say that. All right, so you know lots of examples where they have no, they don't have a viable explanation for lots of effects. And the little radiometer, where you take two objects, you make one of them dark, and you make one of them reflective, and then you try to see if you can measure a difference, because one's reflecting the energy and one's absorbing the energy, that somehow they should spin or it should do something different. But this requires you to have some understanding, too, that the photon didn't care about those effects. The only thing the photon did was hit the surface and in some way change it, and that change can either come out the back end, or the change can come out as a reflection here, or the change can slowly come out as heat radiation. But the change will come out in some way, but you can't necessarily collect it, right? You can't collect the change unless you're right next to the thing to be able to collect it. So no matter what force it collects, the only place you can collect it is somewhere out here. All right, so that's the tricky part, is how do you hit it with something and then also be able to collect the energy from all angles, because it's a little bit tough to do. But anyway, so they found, like, I said, when you have a partial vacuum, this thing will spin, because of, again, how atoms cause more reflections on one side to take place and less reflections happen on the other side. But it just has to do with the fact that there's still atoms in here to screw it up, to give it the idea of you collecting the light energy. You were collecting it all the time, And all you're doing is creating an imbalance between the two surfaces and causing them to spin, but there's the same amount of energies hitting both surfaces. The same amount of change is taking place to both, in the sense that the little demon of the photon is going to leave. The energy of the photon will leave eventually, and it's just figuring out which way it left. you know. But it's hard to say you can conserve. All you have is movement. You can't really conserve direction. I guess there's an argument to be made that direction isn't conserved, just motion. So things can go. Well, I'd say I don't even want to say direction isn't conserved, because inside the electron maybe it is. But that's how far they are from answers to these questions. So it's like they're talking like they know the answer, and they don't know the answer. They don't know how it really works. And so the important one is, again, to get to the perpetual motion thing. So their vision of things is that I throw something into space, and it keeps going forever. So once I give something a velocity, it'll just keep going. Well, the problem is I could argue that electrons don't even do that. So if we create a device to capture electrons, the fact is I turn the pump off, don't keep making the electrons all run out of gas. Even in a perfect vacuum, they just die, they just run out of gas. They can't just stay in here in this nice little magnetic field. They don't do it. They don't do it in accelerators. You accelerate them, and they're constantly decelerating, so you have to constantly keep pushing them to keep them going faster. To get them to go faster and faster, you have to keep compensating for how much they're slowing down. So, where you have evidence that this idea that matter can acquire perpetual motion is only under certain circumstances can matter acquire perpetual motion. That there has to be some mechanism where the energy goes in, as I've described. You could make this theoretical cart where you throw energy in and there's no friction, and the energy just bounces back and forth. And in such a circumstance, the cart would keep moving perpetually. It would stop moving, then start moving, then start moving, then stop moving, then start moving, then stop moving. It would never go backwards. So once you put this energy in, you can capture it, and the energy will keep going this way more than it goes this way. So it'll always, 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 always be going forward. And so it has perpetual motion. And where did it get it from? Well, it got it from the piece of energy it trapped. And it truly trapped it. Like, these traps fail. These other traps we make fail. So all we have is these. We haven't yet made an experiment that I know of on the real micro scale, demonstrating the fact that you can capture entirely a piece of energy. And once you've captured it, you've captured its momentum in a direction. It'll always process, again, like a circle processing. Even if it was caught in an orbit, it's always processing. It always keeps what energy it came in with. Jump a little bit ahead.
Is that without air resistance, if you could imagine...
All right, so this was, like I said, I was doing this for all audiences, I guess. I mean, just, going through old theories of how arrows kept going through the air when we know they didn't just keep going. They did slow down. They do deteriorate, and then gravity pulls them down. So they have both fighting against them. The whole arrow, shoot an arrow straight up, and, it stops eventually, and then it comes straight back down again. So, telling us theories before they even understood gravity is kind of pointless, but whatever.
Through the vacuum, more or less at a constant velocity. Not exactly, because there's outgassing, they're still in the gravitational field of the sun and other things in the galaxy, but more or less constant velocity through the vacuum is...
Right, so you can achieve efficiencies. So especially in like I said, the deeper the space you get into, the higher the vacuum, the less things that'll get in the way of your cart example, for example. I just shine some light, two mirrors, and the light gets trapped in there forever, right? So the idea would be is, yeah, if you did that in space, the forward momentum was always the forward momentum. That's what went, the whatever momentum went in is going to keep winning in the long term. Now, yes, it's going to do this dotted line thing. It's going to stop and then start and then stop and start and stop and start. But the fact is that it will make matter move perpetually. And then if you think about the fact that there's energy coming towards it, that it's going to plow through more energy. So if you do think of the consequence of actual energy existing in the universe, and the fact is that it has real momentum and that you are moving into it and away from the stuff from behind, well, that just ends up compressing the box, which just creates more energy inside the box, because now you have impacts. The smaller I make the box, the more often I hit surfaces, and therefore the more energy I essentially have in the box. So you create energy by changing proximity. So distance ends up being energy when you have something moving and it's trapped between things. Yeah, jump ahead a little bit.
In that straight line until something does act on it. And then the second law, which is the one that is all the work when you solve the equations and do your physics homework problems, is the one that says when you do act on it, here's how the thing accelerates. Acceleration being a deviation from motion at constant velocity. So
again, the idea of motion at a constant velocity really can't work, in the sense that the only way you can theoretically create it is that it won't be at a constant velocity. You'll stop and you'll start, and you'll stop and you'll start, because trapping energy has a consequence. Now, even precession wouldn't be there's a constant velocity around, but in a sense, the precession can only happen when you're going forward. This part of the circle is the parts processing. So, what else? I don't know if there's anything else on that particular point.
Newton had the whole shebang there, but so there's good news and bad news here in terms of what they understood, Galileo and Newton. Galileo and Newton appreciated that things that were moving at a constant velocity would just keep moving, okay? They didn't quite have the words like momentum and energy.
Right, so the difference is what they didn't have was the idea, the concept of matter and energy. So when he says momentum and energy, what does that mean? Where does the matter get its energy from, or its momentum from? It gets it from forces, okay, most of the time. Now, obviously, I can hit, well, like I said, even if I hit two electrons into each other, right? Even conventional physics will argue the electrons this electron doesn't bang into this electron and then bounce off in some kinetic way. That, in fact, there's a pressure created between them, and that this one will deflect off that pressure, and this one will deflect off the pressure. And so there's something else that's controlling the interaction, and there's no the motion will be dictated by something a lot more complex than just two objects moving. So, and then again, you can add force to something by just pushing, having a floor, and then you're standing on it, and something can push you, okay, from your feet up, and you know that what's happening is there's a bunch of chemical pressure that's going to be put on your bones and your muscles and everything else, and it's going to move through you and force all of these things to be pushed. But it's going to be because there's actual physical pieces to you that will bang into each other, so to speak, push on each other to push you. But then you could fall in gravity, or you could be standing in gravity, and a very different thing is happening. The gravity is pushing you everywhere on all your surfaces, but the only place you're going to feel it is where you're hitting the ground. All your surfaces want to be moving, and They're all moving in a direction, and what stops them is the exact same thing that happens here is almost in reverse. There has to be a back pressure that stops them from going anywhere by pushing back. And so you really are moving down, pieces of you are moving, and then they're being forced to move back up again. So instead of thinking that you're just standing on the earth, you're really, your actual atoms and your little bits are actually being accelerated. They are moving down, and you're moving back up again. You're moving down, and you're moving back up again. You're moving down. So you're doing this in the gravity, and the satellite in space is doing the same thing. You know, gravity's pushing it down. It's not doing some perfect little orbit. It's actually winning and losing the battle. But the point is it's doing it much slower than you are because you're in stronger gravity. So this distance, this total distance the satellite travels is a lot less than the total distance you're traveling. And that's why your clock is slow. Okay, the slow clock is the clock on the ground. The fast clock is the one on the satellite. Even though we're supposed to think the satellite's going 20,000 miles an hour, it has a huge advantage on us. We're only going 2,000 miles an hour around the Earth, something like that. 22 miles an hour? No, I think it's faster than that. Well, anyway, we're not going very fast compared to the satellite in this direction. But what we are doing is we're bouncing a lot more. And that higher rate of bouncing is what's accounting for the greater distance we're traveling, because we're doing the actual, our atoms are doing the actual distance. And that's why an atomic clock here is slower than an atomic clock here, because the atomic clock here is moving faster. And forcing a clock to move, certain clocks anyway, cause them to decay at a slower rate because they have less chance of having the little special circumstance that causes decay. See, it's something else they don't even understand. I mean, they use these concepts and they just say them, decay, but they really don't understand what causes decay.
Half mv squared. So obviously, if the mass is constant and the velocity is constant, both of these things are conserved. The hard question is, are either one of them or both of them conserved really all the time?
Squares are interesting things, right? Because you could plug some numbers into there and you get exactly the same answer, right? Like if you put a 4 in there, you know, and say the mass is 1, so you have mass times the velocity. So velocity is 4, so I get 4 as the answer for the momentum. 4 momentums. And if I put 4 in the bottom equation, I get 1 times the square of the velocity, so that's 16. So that's 16, and then half of 16 is 8. Oh yeah, well, that is a bigger number. But anyway, the kinetic energy just has to do with how efficiently momentum is transferred into something. So the idea is that to change the momentum of the matter bits, that is the actual electrons, there's a certain amount of waste in the force. The force can't just apply its momentum evenly or perfectly. And so there's a certain inefficiency in how much actual energy how much you can convert something. So the faster it's going, the more energy you have to apply to make it go faster. And so that would be sort of a simple argument, right? That if you're trying to push something, or even a kid's swing or anything, and it starts going faster than you can push, you can't really make it go any faster. So the idea is when something's moving, you took 10 mile an hour force and you hit something and now it's moving 10 miles an hour. Well, now your 10 mile an hour force can't ever catch up to your thing to actually hit it to apply more energy. So you know that now your force has to be 20 miles an hour to add energy to a system. So the faster something's going, you have to apply more energy to make it go faster, because you have to basically fight the fact that there is drag, that there is a universe fighting against you, creating a whole bunch of this without any of that. I mean, that's what you're trying to do. You're trying to make something do all this. And to do all this, that means you have to get rid of all the opposite thatness that exists. And it's not that easy to do. So the faster you make something go, the more you're going to have to apply more energy to make it go faster. So when it's going faster, the amount of actual energy or momentum you had to use to make it go faster increases. So the actual energy in the thing is higher because it takes more energy now to slow it down also. Alright, we'll go here.
Ball of silly putty in the middle, okay? You could calculate the momentum of each ball of silly putty beforehand. It's a vector quantity, to be technical about it.
All right, so the real mistake in this kind of comparison, so he's comparing pool balls, and they go in certain directions, and it's really easy to follow. And then he uses the example of things that are inelastic. Words are used backwards, unfortunately. So the things that are mushy, and then we can talk about how the energy swirls and it does different things inside of the thing. So it's really just saying, I'm going to look at the really small universe and say, there's these little bits banging into each other, and then the next minute I'm going to make the little small universe into another smaller universe that can collapse and break into electrons and protons and be small again. And it's really not like that. So I would argue there's no correlation to anything in the subatomic level that behaves like silly putty. There's no putty on the tiny scale. The electrons aren't putty. They don't. I mean, they have some complexity in the sense that I would argue they're going to. I mean, there's some point where you have to just say it's the most elemental function, right? But no, there's a function inside of electrons. But I mean, their rules are pretty explicit. This energy goes in, and the electron will do a specific thing based on its previous condition. That is, based on what has hit it previously. It already has a condition it's in, and it will combine this new condition of being hit with the old condition. So it's sort of like the pool ball thing, except the balls are different based on which way they're moving. They're physically different, and they will react subtly different based on their past experience. They've been conditioned by the path they're taking, and that condition will add one more factor to how the force will be interpreted, because they have a bias. But I mean, there's one universe, and there's, I would argue there's no silly putty in it. The little tiny universe doesn't have any bits that do this inelastic thing. There's all just really efficient, mechanical, right turns, left turns, up, downs. I mean, really, really explicit kind of reactions.
And they could smack together, and you could calculate the momentum of the total big ball, and it would be the same.
Right, so this is something you could calculate it, but this is the part where it gets experimentally difficult. So I'd say even something as obvious as polarizing film, right? I've never seen an experiment where they take the polarizing films and they put them this way, they cross them, and then they measure the temperature of the films to see where did the energy go. Because they're saying the photons are being absorbed by the film. Essentially, that's why they're not getting through, is because somehow they were absorbed. Well, if they were absorbed, if the energy and the momentum of the photons was absorbed, then the material should get hot. They should be able to detect the thermal radiation. They should be able to detect something that would indicate that the momentum didn't just disappear. So they talk this conservation, but they can't really prove the conservation. They just say our equation says so. But that's not really good enough. And they really don't have equations covering all these other subjects. Again, they don't have a rational theory of how a photon is affected by polarizing film, just like they don't really have a rational theory of how a slit affects photons.
French. Now, to be honest, I'm not sure whether she translated from the original Latin or from an English translation.
Okay, so this is more little storytelling, which really, fine, whatever. Yeah, she was a really accomplished woman, died in pregnancy. I mean, having a baby, which was a really big mistake at 40 or whatever. So just another throwing a little anti-natalism there. Killed a perfectly good scientist for a dumb reason, and such. Wasn't her husband's kid either. Blah 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 blah.
But what you can see is a neutron turning into an electron and a proton and an anti-neutrino. So neutrons charge 0.
Right. So they just make up this neutrino stuff, and so let's just understand what they're doing. In terms of they want to create some sort of energy conservation, but they can only understand the energy as being in the form of some particle thing. They don't understand that part of the energy is just the force itself. And so I don't know exactly how to explain this, but so you have an electron and a proton, and they're in some configuration that makes this a neutron, right? I mean, that's the basic conclusion is that a neutron is really just a proton and an electron in association with each other in such a way as it's a nice little compact package, and that from the external world you can't see the positive and the negative charge. They're both, either it's spinning, it's doing something where it makes its charge unperceptible. So I would argue that yes, it's just spinning and it's just radiating purple, and purple looks like neutral. There's no red, no blue. So if you made this red and you made this blue, you can't see the red and the blue because it's purple. And that's why we call it neutral. But it's not really neutral. It's made of an electron and proton. And so what happens is that they see this decay, but they have to account for the fact that what's really happening when it decays is something's happening to force the proton and the electron are now way apart. All right, so when it decays, the two bits are being separated, and then it took a force. All right, you don't get that for free, right? They don't just separate for free. They separate because something causes them to separate, to go from their native state, which might be a state where more pressure exists, right? So you could argue that all I have is more pressure on them from the external conditions, and all I do is, through some mechanism, create less pressure. That is, I evacuate and I create some sort of circumstance where there's less pressure from the outside. And so now they invent this neutrino thing, because what the neutrino is accounting for is the energy it took to separate them. That is, whatever they did to separate them is what they're measuring it as an output component. When, see, if they understood conservation, they'd understand if I'm going to change a system, the change is gonna have to come out. Like everything has a change equilibrium kind of thing. So yes, of course, that change will be detected in your out byproducts, but that change is a byproduct of the fact that you caused this change. So when you split these two, you put energy in, that's the neutrino coming out. But there is no such thing. There's no neutrino. There's a quanta of energy, okay, that is the byproduct of separating an electron and a proton. Energy comes out, not a neutrino. There's no particle. There's no place for a neutrino to exist. There's no, all of their extra particles, you can just understand, there's no room for them inside the atom. The atom's already full. Protons, neutrons, electrons. We've already accounted for everything. There's no place for all these muons and neutrinos and antiparticles and there's no room for all that crap in there. We've already accounted for the mass of objects.
Protons charge +1, electrons charge -1, neutrinos or antineutrinos charge 0.
Right. So just forget that part. No, there's no evidence of a neutrino. There's no evidence these things exist.
This is circa 1800. And Laplace came up with the famous Laplace's demon thought experiment. Laplace says, imagine I have a vast intelligence that is so smart it knows the position and the velocity of every particle or every bit of stuff everywhere in the universe.
Right, and it's not that hard to do, not for the whole universe, but for small-scale objects, we can sort of get it, right? We get it that, okay, there's 1 trillion atoms in here, and blah, 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 apple to the earth kind of comparison, lots of atoms in here, lots of little stuff going on, stuff moving around. So we can take a smaller system and get the idea that there's nothing poofing in here. But they don't believe that. I mean, they think extra space is poofing in there, right? There's a whole bunch of extra space being created inside of every object. It's all running away from each other to some extent, some little tiny a bit, but there's just this extra amount of pushing happening in there somehow. Pushing everything apart. Every little atom is moving away from every other atom. Some mysterious reason. And then they have all these quantum effects happening. All these little bits that just, this one says I'm white, and it's forcing this other guy to be pink, even though he doesn't want to be pink. All kinds of magic going on inside of there, where I would argue that we can sort of understand the system and say, no, there's pressure around everything. The entire universe is full of this pressure, and what you can do is you can filter the pressure, and that's where you get this positive and negative thing. And once you have two negatives next to each other, that means they're sending the same radiation at each other, and it reflects off them. So you can't push them together because the energy's bouncing back and forth, and it gets stronger and stronger and stronger. The closer I make them, the more impacts on these objects, and that's repulsion on the charge scale. And attraction would just be the opposite, that all the energy that's between them passes out of the object without reflection, without getting back to it. And so there's nothing in between them to pressurize, and the external force will push them together. So, it can be understood, in terms of just making a little mechanical system and making it understood, and making an understanding. We see it in the real world. Again, I could just use the analogy. Your theory and my theory might be that when you roll dice, physical things happen to the dice. The dice actually have completely conservative interactions with the world. They bounce. The impacts are very reliable, mathematically consistent. Certain things will happen, and there really isn't any magic to it. There's no place anywhere in it where we have to say, oh, there's some unaccountable force. It's all understandable, and you'll end up with a byproduct. And you can test the theory just by flipping coins, right? I mean, you can just flip them a little bit, and every time you can flip a head. Every single time. One flip, heads. One flip, heads. Very reliable mechanics. So yeah, if you know the preconditions, you can predict the outcome perfectly. And there's nothing in there that's going to be irregular and cause any effects. But that's not what they believe. So they believe that all this little scale stuff is doing all of this random magic, and that there is some reason to believe that even though I did it exactly the same this time as I did it the same, the conditions are identical, that somehow the result's not going to be the same. They believe that, but they don't believe it for a good reason.
And then furthermore, it has enormous calculational capacities, so we can solve Newton's laws. To that vast intelligence, which was later dubbed Laplace's demon, he never called it a demon.
Right, so you don't need a vast intelligence if you just cut out a piece of the universe. So just the solar system, for example. Right, so just make your experiment just the solar system. If I know where every little speck is inside the solar system, every piece of energy, if I count for every single little bit in there, is it possible that I can arrange it exactly the same way and have it do something different? And I obviously would argue it would be silly for me to think it's going to be any different.
Laplace's demon. To that vast intelligence, Laplace says, the future and the past are as fixed and known as...
All right, so even saying fixed is silly. Of course the past is fixed. It's the past, for fuck's sake. I can't be here without it being fixed. I can't have a shape or a form or an identity or an anything. So, I mean, it's just kind of silly to talk about how fixed the past is. But, yes, the point is that the future, nothing is really in any way probabilistic. It's really just inevitable. the probability just comes in terms of I make enough variables, I can't follow the inevitabilities anymore. And it looks like probability, but there really is none.
The present moment is. That would not have been a feature of Aristotelian physics. This is something new. And there's no place in that story for purposes or
I don't even think that's true about Aristotelian. I mean, obviously they believed in the first mover, but the first mover, again, is we're stuck with the same argument. We're not talking about what caused the first motion. We're talking about once the motion is in process, does it follow these explicit rules? And there's just no other rule. There's no magic rule. There's no real random. There's just inevitable outcomes for preconditions. Every precondition has an inevitable outcome. And that's just it, you know. You can't, there's not enough room for any confusion about the outcome. And that's all you're really creating, right? Is the flip the coin thing, right? If I just flip it a little bit, just flip it so it takes one turn and it lands on the ground. I can do it, it's perfectly reliable. And no matter how many times I do it in the universe, it's always going to come up with the same result if I do the same amount of flicking. So it's perfect. And the only thing that makes it at all complicated is that if I flip it harder, then I have more variability in how hard I flipped it. So the harder I try to flip it, the more variability in exactly how much I flipped it, and now my results aren't going to be as consistent. And so now I'm going to get lots of variable end products because I'm going to have a variable in how much flipping I'm doing. But if I can precisely control exactly how much energy goes into the flip, I can precisely predict, no matter how many flips it takes in space, what the outcome's going to be. And that's just the truth. Because we know all the mechanics that exist. There's nothing, so it's not really probability. It's inevitability every time.
Natures. What there is a rule, a set of rules, which we call the laws of physics.
So again, this purposes stuff it's not a useful scientific term, right? That's a utility term or some other kind of stupid, concept of what we value, and that doesn't have anything to do with the fact that everything that's taking place, every sentence I'm speaking, all of it, was already decided it was going to turn out that way 100 years ago, 1,000 years ago, 1,000,000 years ago. There's nothing in the system that changes, that creates some real random variable. There's no such thing. They believe that. They don't have any evidence for that, and yet they say that we understand this concept of momentum and conservation. Well, the conservation of the rules is, you can't defeat the what goes up comes down thing. You can't defeat the simple rules that everything is obeying. And the rules on the subatomic level are really simple.
Which say, given what's happening at one moment, we know what will happen toward the future, and we know what did happen in the past. Now, of course, modern physics is going to mess this up a little bit. It's not that it went away, but it becomes...
Yeah, no, it's ruined. It does go away. How does it not go away? All I have to do is make the system small enough, and you're going to make it completely random. You're going to make it some sort of real random. Like somehow there is no predictive tools because there's no predictive circumstance, and the outcomes can be black or white. And there's not a rule that decides black or white. And I just say prove it, and you haven't come close to that burden. So you're making an extraordinary claim that you believe there is magic, randomness, but you haven't proven it with anything.
More subtle and complicated, and we will talk about that in future episodes, future big ideas that we'll get to. But
silly ideas. So they're going to be big, silly ideas. So I guess I'll inject that word into the conversation because yes, they're going to be silly ideas.
The shift in perspective lingers on, and I think is the important thing here. The universe is sort of a mechanism. This was called the clockwork universe, right? That's what they actually refer to it as. The universe is no longer, in this perspective, alive. The
universe isn't alive, right? So again, what is that? This isn't rational conversation. So alive means that you're somehow a random generator. So I guess that's the implication, that we have to have our free will and we have to have all these mechanisms that are nonsensical and can be demonstrated to be nonsensical if you recognize what we do know. I mean, the facts do indicate that there's just no room for it. The cats aren't dogs. I mean, you can you just say it just doesn't turn out that way. Sorry. You can want your Schrodinger cat to be in all these states, but it's really not. It's just a story you can tell. It's just a fable you can make up about reality that it turns on and off. But it doesn't, or it makes multiverses or all this other nonsense. But anyway, it's just silly.
Just is obeying rules. So a new problem arises. How do we understand ourselves as living beings in this universe, which is...
Yes, we understand ourselves to be programmed robots. We're just part of the Earth Borg. And that's all you can be. You can only be a byproduct. And even in your dissent against the Borg, and I would dissent against your Borg, well, it was inevitable that I was going to do that because you left enough loopholes and enough unanswered questions and enough reason to doubt for doubt to show up. For me to cling and grab onto those pieces and be moved by them because they're real things that exist. The weakness of your evidence is why I am believing you are silly. That's the reason, okay? It's not some other reason. There's not some quantum reason. The reason it happens is the banana peel. Somebody has to step on it and they slip. They miss the banana peel, they don't slip. I mean, there's causes to every effect. So everything that exists because of reasons. And if you can understand the reasons, then you can have some hope of interacting with a system like yourself in some way that will make the system do something you want it to do. You can apply the magnetism in the right way and make the motor spin. You apply it in the wrong way, this doesn't spin. There's just rules to every interaction we have in terms of what will work and what won't, how you get somewhere, how you don't. And they're just facts. I mean, you could say there's just rules of being, selling somebody something. Rules that you have to follow to gain their confidence, to, shyster them. And those are just facts. They're just rules. Because it is a fixed, hard, physical universe we exist in. And so, yes, we're just robots.
Tell each other.
Programmed by environment to make different kinds of noises.
A farmer asks for advice from a physicist about how to maximize the milk output of his herd of cows. Physicist goes off and thinks about it and then comes back a few days later.
Right. So this is just the idealized argument, like turn everything into an idealized thought experiment or whatever. But there's some value to that, right? I mean, is there some value to saying think of a frictionless system or this or that? Because those systems can exist in other places we can't see. So that's perfectly valid. But to say everything, you're going to deny the rules that are fundamental to the function, well, then, you're going too far.
It says, okay, I've got it all figured out. First, assume a spherical cow. Now, to a farmer, that does not sound like a very good idea, a spherical cow, right? Like, cows are not anywhere near spherical.
Yeah, I know, but their milk bucket is. So it sort of works out in a sense. But whatever, you could argue there is some point in it. And the principle is still going to be fundamentally the same. You're just making the math easier, essentially. So spherical symmetry makes everything a lot easier. You can get rid of all the nuances and waste of the other different shapes. So it's just, easier. And you lose some accuracy. Well, anyway, that's a minor fine point. But the point is that physics is in abstraction. What the real point is that they do this with ideas like, bent space and having an infinite supply of gravity. Do they know there's an infinite supply of gravity? There's an infinite supply of attractive force or repulsive force? I mean, they really don't think that, right? They don't think that you can have an infinite magnet or you can have, have infinite charge. So why do they think you can have an infinite amount of gravity, right? So, these are places where their mathematics shows it's incomplete in the sense that it's really not describing the real world. It's describing a world that is missing real features. And I would argue it's a real feature that there's only so much gravity you can glean. There's not an infinite supply. But anyway, probably enough of a video and such. So we'll see what the next subject is. But yeah, he really didn't talk about momentum, in any real sense. He just talked about the theory of understanding a concept, and he didn't really touch on the hard part of the concept. So till the next time and such and so forth and whatnot. And there really, there's lots of experiments that need probing. So you could probe this slit experiment. You could probe the electron experiment, where you trap the electrons in a magnetic field. You could take the cathode ray tube stuff and which way the magnet makes the beam move. All of those experiments need more probing, more poking, to find what's missing. Just like the radiometer, with the little spinning stuff. It's a very subtle difference. An 8 vacuum, it spins. A 10 vacuum, it stops spinning. That kind of thing. I'm not using real numbers, but I'm just saying the stronger you make the vacuum, the less it spins. Kind of a funny thing, right? It spins more as you're making the vacuum, and then it stops spinning when you make more vacuum. And, that's evidence of something. So that's the kind of probing they need to do these other experiments to find out what's the nuance, what's the trick. What's the trick? The trick of it. And they're not really too interested in finding out that the trick is a physical reason. Because they really want to believe, that they've captured perpetual solar energy or something. Or they've found a place where they can get energy out of a system for free. Anyway, till the next time and such.